Gas injection problem. Various mechanisms for gas migration have been identified. Gas diffusion, two-phase flow, and two-phase flow coupled with mechanical effects that may lead to fracturing of the porous medium. This example addresses the gas injection in a very stiff porous media. First of all, as always, we select data problem type code bright, and now we are going to define the geometry. The geometry is a cylindrical sample of a mixture of sand bentonite, and taking advantage of the symmetry, only one half of the diameter is simulated. So go to create line icon and enter the coordinates of the external points that are 0, 0, 0.03, 0, 0.03, 0.12, and the last one 0.12. Press the join button and press escape. Now it's necessary to create the points on which the gas will be injected on the left boundary and the points of the liquid output on the right boundary. To create these points, go to Geometry, Edit, Divide, Lines, Near Points, and we have to enter the coordinates of the point that we want to create, 0, 0.04. Then select the line in which that point is located and repeat this process with all the points that we are going to create in order to divide the lines. The coordinates of these points are 0, 0.04, this is the one that we have already introduced, and 0, 0.06, 0.08, 0.03, 0.03, 0.03, 0.06, and the last one 0.03, 0.09. So we repeat this process, entering all the points and selecting the corresponding lines. And once finished, we have the 3 points on the left boundary and the 3 points on the right boundary. So here, introducing the last one. Select the line, and we have all the points created. Now go to View, Label, All in points, all in lines, and View, Label, All in points in order to visualize the labels of the created points and lines. Now we have the geometry with the corresponding numeration. And to generate a surface, go to Geometry, Create, Nerve Surface by Contour, and select all the geometry, press Escape, and the surface is created. Now we're going to define the attributes and conditions. It's a good idea to save the work. Now, as always, go to the Save icon, select the problem name, and click Save. Now go to Data, Problem Data, and in the General Data tab, introduce a name for a title for the problem, then choose Full Execution from the Execution drop-down menu. No backup for the Backup menu, select around y-axis in the axisymmetry option and enter the value of 0 in the theta field of the gravity component. Now go to equation solved and check the box of mass balance of water and mass balance of air. This implies that the air concentration is computed. Now select the solution strategy tab and enter 1 for the epsilon and theta boxes, 7 for the time step control box, 10 for the max number of iterations per time step. Now choose direct LU back 3 from the solver type drop down menu. Leave by default average nodal degrees of saturation in elemental relative permeability and set a value of 1 exponential minus 5 in max abs PL, 1 exponential minus 10 in max node water mass val, 0.1 in PL ether core, and 1 exponential minus 5 in max abs PG, 1 exponential minus 10 in max node air mass val, and 0.1 in PG ether core. Leave the default option of the convergence criterion and go to the output tab. Choose all from the write numerical process information, type 20 in the writing frequency box, choose Gauss points in the output points, and write all information has to be checked. Click accept and close. We're going to define the materials now. Go to data, materials, and create a new material using the new icon. Name it sand bentonite and click OK. I'm going to introduce the parameters that define the material now. You can skip this part. Once finished, save the material and assign this material to the surface created before. Click Finish, close the materials window, and let's define the conditions. Go to Data, Conditions. Let's start with the hydraulic boundary conditions that should be imposed on points where the gas is injected and on points of flow output. In the point icon that is already selected, we are going to choose Flux BC from the drop-down menu, and we're going to insert on the nodes 5, 6 and 7 a prescribed gas flow of 1 exponential minus 9. So we're going to enter this condition and assign it over the points 5, 6 and 7. We select these mentioned points, click finish, and now for the flow output we are going to introduce or return by default to the prescribed gas flow and introduce a prescribed gas pressure of 0.1, a gamma for gas of 1000, a prescribed liquid pressure of 0.1, and a gamma for liquid of 1002. Here we are introducing the prescribed liquid pressure 0.1, gamma for liquid 1000, and we're going to assign this condition to the nodes 8, 9 and 10. These are where the flow output is. Finish, and now we can select draw flux BC to visualize the conditions assigned. Now let's assign the initial unknowns. Go to the surface icon, select initial unknowns from the drop down menu, select constant from the distribution drop down menu, that's already selected. Introduce 0.1 in the PL field and 0.1 in the PG field and 20 in the temperature field. We are going to assign these initial unknowns to the only surface that we have created. Now click finish, and we're going to introduce the initial porosity. Select initial porosity from the drop down menu, introduce 0.3 in the porosity field, the only one, assign it over the same surface, click finish, and now let's see a summary of all the boundary conditions. Going to entities, all conditions. Here we can check that everything we have introduced is okay. Now click close, window 2, and we're going to define the interval data. We only need one time interval due to no changes in boundary conditions during the test. So go to data, interval data, select hours in the units of time discretization, type 0 in the initial time field, 1 in the initial time step, 240 in the final time field, 1 in the partial time and 1 in the partial time step field. Click accept and close. We're going to consider a period of 240 hours to reach an equilibrium condition. So now let's define the mesh we are going to use. Go to mesh, element type, quadrilateral, and assign this type to this type of element to the surface. Now press escape and go to mesh, generate mesh. Enter for the size elements to be generated a value of 0.005 and click OK. We're going to use a mesh composed by linear quadrilateral elements. Now this window displaying the mesh information appears, and click View Mesh. This is the mesh that we have defined. Now it's time to process. Go to calculate. You can go to calculate view process info in order to view the information while the software is simulating the problem. Now the process is finished. You can access the post-process interface using post-process button. We're going to analyze the evolution of the main variables of the problem. Go to Window, View Results, and select Contour Field from the View drop-down menu. And we're going to present the contours of the dissolved air concentration, gas density, gas pressure, liquid density, liquid pressure, and degree of saturation at some specific times of the analysis. You can use the animate feature to view the evolution of each parameter in the time steps considered by the problem. From the results of the mentioned variables, we can highlight the following points. Gas pressure, gas density, and dissolved air concentrations increase considerably near to the gas injection points at the test beginning. In time, values are reduced and an equilibrium condition is reached for all variables after about 6 hours. An effect of wave propagation in the medium is observed in the time variation of the variables controlling the problem. The same tendency is observed for the liquid pressure and liquid density. However, the variation of the liquid density is very small, and values reached of the liquid pressure are smaller than of the gas pressure. At the beginning, the porous medium is saturated, which means that the degree of saturation is equal to 1. It will be observed that due to the gas injection, the medium becomes unsaturated. The water is displaced by the gas or air in a progressive way, and at the end time of the test, 240 hours, the degree of saturation has been reduced to 0.85. And now we're going to create some graphs of the time evolution of some variables. To do that, go to the graph icon, select the point evolution, and select first of all the gas pressure. Now we have to select the points we're interested in. We're going to select the first one 0,0.06, the second one 0.015, 0.06, and the third one 0.029, 0.06. These points are for all the three graphs that I'm going to create. This is the first one, the point evolution of the gas pressure. It can be seen that after a period of injection, gas starts to penetrate into the medium. A gas pressure build-up occurs, and both a peak threshold gas pressure and liquid pressure are observed. These peak threshold pressures are higher at the point P1, the injection point, and occurs at a lower time period in comparison with the observed for the points P2 and P3. So we're going to create the same graph, but for the liquid pressure this time. We select the 3 points. I'm selecting the points in the graphical interface to make it quicker. You can enter the coordinates on the message box. And we can appreciate a similar graph of the liquid pressure that the one we have seen for the gas pressure. So they both reach a steady state after 6 hours. And now I'm going to create the third graph for the degree of saturation. So as before, select the point evolution, degree of saturation, pick the 3 points. Here you can see that the first one is near the central point of injection, the second one is in the middle of the sample, and the third one is very close to the central point of the output flow. And here you have the graph of the degree of saturation, the evolution in the 3 points. So that's all for this tutorial. We're going to continue in the second part, that is with the hydromechanical analysis.